energy is a commodity, I think, in this world. So if too much energy is required, well, that process is simply not going to happen. Okay, so for magnesium, magnesium forms a cation of 2 positive charge. Magnesium is in group 2A. The number in red, they're correlating with one another. Okay, group 2A, 2 positive charge. Group 1A, 1 positive charge. Group 3A, 3 positive charge. So for the main group elements, metals, the charge equals to the group number. And if you look at this particular table there, we're looking at second period, third period, fourth period, group 1A all the way through group 8A. You see a general trend. Removing the first electron in group 1A, well, group 1A only has one valence electron. Removing the first electron requires 513 kilojoules per mole of energy. For lithium, if you try to touch the core electron, you can see the energy requirement is increased by more than tenfold. If you touch the third electron, core electron, it's even more difficult. Therefore, for lithium group 1A, you can only take away 1 electron. Similarly, for sodium 496, 4562, 6912, you can remove 1 electron. Don't touch the core electron. Too much energy. For potassium 419, 3000, 4000. Remove 1 electron, don't touch the core electron. So group 1A, you can only remove 1 electron. Group 2A, the first 2 ionization energy are pretty close to one another. You can remove 2 electrons there, but don't touch the core electron. You see that pattern throughout. That's a periodic property. You also see within the same group, it's getting easier to remove that first electron. 500, 490, 410, 420. Okay. As you go down in the group, in the period there, from top to bottom, within the group there, okay, as you go from top in the group to the bottom of the group there, it's getting easier to remove the electron, meaning they're more reactive and requires less energy. So that's something that we will talk about in the periodic property of ionization energy there, and you see that trend throughout the numbers in the data presented in this particular table there. Okay. Depends on the period, depends on the group that they're in. Ionization energy is increasing from left to right, from top, well, decreasing from top to bottom. That's the trend that we need you to memorize. That's part of the memorization you have to do in chapter 8. Okay, so in this case, and this is the table, well, this table is actually, I copied it from a different textbook there. And this particular table indicates, say, for the elements in group 3A, in the third period there, and going from sodium all the way to argon, you can see the steps, if you will, in terms of the ionization energy, IE1, IE2, IE7, so on and so forth. And it's easy to remove the electrons. For group 1A, you can take 1 electron away. Group 2A, these two are considered comparable. And if you try to remove the third electron, this one is much higher. So the pink region refers to the energy required to remove the core electron. And the core electron energy, removal of the core electron requires much higher energy. So the electrons are only going to be, you're only going to be removing the valence electrons in the chemical reaction. Okay. Now the thing here is that ionization energy is an endothermic process. So ionization energy is always going to be a positive number. You have to supply that energy in order to remove the electron. Okay. So the other part that we want to talk about though, ionization energy is the process of removing electrons. What happens if you want to give a particular element an electron? Well, the term that we use to describe that process is electron affinity. Electron affinity is the energy involved. In this case, it could be a positive number, endothermic. It could also be an exothermic process, negative. So energy can be released or absorbed in this process. But electron affinity, EA, is defined as when an electron is attached to a gas phase atom to form an a negatively charged ion. Now, some elements will be happy, some atoms of some element will be happy to take in that electron. Example, chlorine. Chlorine group 7A, you have 7 valence electron. If you give chlorine atom one more electron, chlorine atom will say, thank you, I like that electron. I will give you some energy in return. So the electron affinity, this is actually an exothermic process. Okay. Electron affinity is negative 349 kilojoules per mole. Okay, so that's an exothermic process. Now neon, if you try to force an electron to neon, neon is a group 8A element, it's a noble gas element. Neon is pretty happy with what he has. And if you try to force an electron to neon, you have to supply some energy. So the electron affinity in this case is a positive number. It's an endothermic process. So as we said, ionization energy is always going to be positive. You have to use energy to remove electrons. But when you try to attach electrons to different elements, or depending on who you are trying to give the electrons to, the electron affinity can be a positive number or a negative number, meaning it can be an exothermic or endothermic. Okay. But ionization energy is always positive. Ionization process is always an endothermic process. It always takes energy to remove the electron. Okay, so that's the definition that we want to give you before we get into the topic of periodic property. We need to know how we define these terms. Okay, and then the next learning objective, we are looking at the periodic trends. In terms of electron affinity, ionization energy, atomic radii, ionic radii, the size of the atom there, okay, and among other things. So a lot of memorization is going to be involved in this particular part. We need you to focus on what we're talking about for each of the properties there, and we want you to memorize in the periodic table, going from left to right within the same period, going from top to bottom within the same column, within the same group there. What happens to the ionization energy? What happens to the electron affinity? What happens to the size of the atom, the size of the ion? So, looking at the trend in first ionization energy, pretty much the ionization energy, whether it's first, second, or third, it follows the same trend. Okay. And the trend for first ionization energy, going from top to bottom within the same group, you see the numbers coming down. So the ionization energy is decreasing within the same group from top to bottom. Every time we use the term across the period, we are talking about going from left to right. Okay. And if you look at the trend there, going from left to right, the ionization energy is increasing. And that's the general trend. And there's always an exception there. And if you look at this particular element, boron versus beryllium, beryllium 899, going from left to right, boron 801. That's an exception there. Okay? So what we want you to memorize is, in general, when you go from the left to the right across the periodic table within the same period, the ionization energy is increased. Meaning, taking electrons away from metal is easier than taking electrons away from non-metal. It's the most difficult thing to do when you try to take electrons away